Okay, we'll be going through the nodes of machine learning system optimization, key concepts and models. Uh, the nodes cover fundamental concepts in ML system optimization, including parallel programming models, sequential and parallel algorithm design, and performance metrics like speed up. The session focuses on various parallel programming models, which include pipelined, data parallel, task parallel, and request parallel models. A key performance metric discussed is speed up. Algorithm design sequential. Before delving into parallel models, it's crucial to understand sequential algorithm design, typically based on a generic machine model. Generic machine model or random access machine model. At its core, a computer system for executing instruction consists of a CPU and RAM. The program counter within the CPU tracks the next instruction to be executed. RAM is characterized by a uniform cost of access across all memory locations. I'll just repeat that for more effect. RAM is characterized by a uniform cost of access across all memory locations. So no matter what memory location you access on that RAM, it's uniform. It takes the same amount of maybe time or effort or cost processing power to access the memory locations anywhere on a RAM. Typical instructions executed by the CPU include arithmetic logic operations, load store operations, move data between CPU registers and memory, jump or branch operations, controlling program flow. Executing an instruction stages. Instruction execution is broken down into several distinct stages: fetch instruction, decode instruction, load data, execute, and store the result. So, fetch instruction is fetching the next instruction, indicated by the program counter, is moved to a CPU register. The CPU decode instruction, the CPU identifies the operation or operator to be performed and the address of the data involved. So, where the data is and what operation you have to do. Yeah. NOR, XOR, and whatever. Load data. If the operation requires data from memory, that data is moved into a CPU register. Execute. The actual operation, arithmetic logic, is performed as part of execute. And store result. The result of an operation is moved back to memory. Instruction execution stages. So we've discussed this. Fetch instruction, decode instruction, load, execute. Instruction pipeline. The concept of pipelining arises if separate circuitry is designed for each stage of instruction execution. The concept of pipelining arises if separate circuitry is designed for each stage of instruction execution, and each stage approximately takes the same amount of time, right? So there are different stages: fetch instruction, decode instruction, load, execute, store. And separate, if a separate circuitry is designed for each stage, separate circuitry for fetching instructions, separate circuitry for decoding the instruction, separate circuitry for loading the data, separate circuitry for executing the operations, or separate circuitry for storing the results, then that's managed somehow through pipelining. How that we'll read through. This allows multiple instructions to be in different stages of execution simultaneously, much like an assembly line. For example, a sequence of instructions would be in store stage. For a, let's assume this, that for a sequence of instructions I1 to I5 and so on, I1 would be in store stage, I2 in execute, I3 in load, I4 in decode, and I5 in fetch concurrently. Throughout throughput improvement, if each stage takes one clock cycle, pipelining increases throughput significantly, because in within that one clock cycle, 5 are moving through different stages or maybe taking a step in each of this. So sequential is one instruction per 5 cycle for a 5 stage pipeline. And if it is pipeline, then it is one instruction per one cycle. That's the ideal case. While throughput increases, turnaround time, aka response time for a single instruction, does not necessarily decrease. It might even slightly increase due to the pipeline overload. So even if like throughput is more, it doesn't mean that the response type is more, because then you have to load all of this, carry this load. So that might increase the response time. Modern processors since Intel Pentium circa 1991 typically incorporate deep pipelines, often with more than 5 stages. Pipeline throughput and cycles per instruction CPI. Throughput in processors is measured in CPI, right? So throughput in processors is measured in cycles per instruction. How many cycles are run per instruction? Okay, so let's see what it is. For an ideal pipeline design, the cycles per instruction is 1. This means on average one instruction completes every clock cycle. Now what does this mean? This means on average one instruction completes every clock cycle. In practice, the cycle per instructions may be greater than 1. In practice, cycle per instructions may be greater than 1, but modern designs aim to keep it close to 1. Speed up for a K stage pipeline is ideally K. Factors that may slow down the pipeline or increase the cycles per instruction are as follows. Imbalanced stage times. If some stages take more time than others, the entire pipeline is bottlenecked by the slowest stage. Here earlier in the example, we assumed that it is 1 clock cycle. But if say, one of those was 2 clock cycles. So what are we saying? That if some stages takes more time than others, then the entire pipeline is bottlenecked by the slowest stage. Memory access time. Load and store operations often take significantly more time than other stages, which can slow down the pipeline. Modern pipelines are designed to make most stages take similar times. Okay, so modern pipelines are designed to make most stages take similar times except for load or store. I'll repeat that again. No? So load and store operations take significantly more time than other stages, which can slow down the pipeline. So modern pipeline are designed to make most stages take similar times except for load and store. Memory access and pipeline throughput. So earlier, what all that we discussed in the earlier model was earlier point was pipeline throughput and cycle per instructions, and here we are going to discuss memory access and pipeline throughput. Processor speed is significantly faster than memory access speed. So processor clock cycles are typically 2 to 3 gigahertz, meaning in processor operations might take 0.33 to 0.5 nanoseconds. DRAM, main access memory, takes around 50 to 200 nanoseconds. And SRAM, it's access, which is cache. If the data is available in cache, access can be 5 to 10 nanoseconds. This speed disparity highlights why memory access is a major bottleneck. So mitigation strategies. What are the mitigation strategies for this memory access bottleneck? Multiple levels of caching. Modern architectures use hierarchical caches, SRAMs, to store frequently accessed data closer to the CPU, significantly reducing effective memory access time. Compiler and processor collaboration. So compiler and processors work together to minimize the frequency of memory access operations, right? So what happens through compiler and processor collaboration is compilers and processors, they work together to minimize the frequency of memory access operations. Asynchronous store operations. What are asynchronous store operations? To avoid stalling the processor while waiting for data to be written to main memory, store operations can be executed asynchronously. Right? There are store buffers, buffer registers inside the processor temporarily to hold the data. This allows the processor to continue executing subsequent instructions without waiting for the data to be fully transferred to memory, as the transfer happens in the background without direct processor involvement. Right, so the processor is not involved in loading the data. It happens in the background, and it focuses on uh, executing subsequent instructions that are in the store buffers. Software pipeline. The concept of pipelining is not limited to hardware CPU instructions executions, but can be applied to software design, and I think that's how it came into software pipelining when it transferred to multi-threading, multiprocessing, all of that stuff. It involves breaking a long task into multiple stages. The goal is for these stages to take roughly the same amount of time. If there's a stream of data to be processed, this stream can be fed into the software pipeline, leading to improved throughput. Now, algorithm design. Okay, so what we discussed until now was that sequential algorithm design, right? Now we are going to discuss parallel shared memory model. Shared memory model. In this model, multiple processors P1, P2, and so on, or cores, for example, a multi-core chip, right, shares access to a global shared memory through an interconnection network. Right, so there is global shared memory and multiple processors access to the shared memory through interconnection network. Multi-threaded programming. So apart from shared memory model, what's multi-threaded programming? A common approach in shared memory environments where each thread runs on a separate core. Right, so you divide this pipeline into different stages, and then run each of this stage as a thread on a separate core or a separate processor. Target environment typically refers to a multi-core chip. Then we have top-down design, a general approach to problem solving, also applicable to a parallel algorithm design, is divide the problem into subproblems, find solutions for these subproblems, and combine the sub-solutions. This process can be applied recursively, meaning each subproblem can be further divided. Stopping condition. Now, division stops when atomic problems are reached, which are problems with known solutions. Not just any decomposition works, okay? So there are some constraints. Not just any decomposition works. One must divide only if you know how to combine the solutions effectively. Top down design. We talked about top down design as decomposition. Now we are going to talk about top down design parallel considerations. In parallel top down design, additional factors become crucial. Combining strategy. Knowing how to combine the solutions is paramount. Mapping to processors. How are the subproblems assigned to different processors? Combination location. Where, on which processor or on which core is the combination of sub solutions performed? Number of subproblems. This is often related to the number of available processors. Processor utilization. Now, this is a key factor. Generally, more processors imply more subproblems to effectively utilize them. Now, we will take an example hierarchy. A main problem P can be divided into P1 and P2, which can run in parallel. P1 can then be further divided into P11 and P12, and P2 into P21. Okay. Now all of P11, P12 and P21 can run in parallel relative to each other. So this is kind of an hierarchy. We understand that. Data parallel programming or single program multiple data. Now this is one type, right? So algorithm design, sequential sort of pipeline. Then there was this parallel shared memory model. Right, algorithm design was one was sequential and one was obviously parallel, and within parallel we had many times the shared memory model, multi-threaded programming, top-down design decomposition, top-down design, parallel considerations. Now we have data parallel programming or single program multiple data. I think this is now what we will allude to big data, all of that, right? Definition of data parallel execution or computation. It involves the same task executing independently, that is in parallel, on different subsets of data. The overall data is divided into roughly equal sized subsets. The same task is replicated and run on different processors, with each processor handling a distinct subset of data. This model typically assumes a shared memory model. Okay, typically assumes a shared memory model where all processors can access the global shared memory. Dividing data might simply involve setting boundary markers for different processors. 1 to 5, one processor, 5 to 10, another 6 to 10, another processor, 11 to 15, another processor, and so on. Now, what are the examples of data parallel execution? Searching a key in a list of size n. Assume list 0 to n minus 1 is in shared memory. For a processor P, each for a set of processors, for preprocessors, right? Each processor searches a sub-segment where, let's say I have 100 list of 100 elements and I have 10 processors. So I'll do that 100 by 10, so which is one processor will search for 10. One processor will search for a subsegment of 10 elements of the list. Processor P0 then combines the results by performing a logical AND operation on result values. This clearly shows the same search task on different data subsets. Another example is fingerprint matching. Matching a given print F against a database D of n prints. The database D is divided into P parts, and each processor matches F against its assigned subset of D. Vector product AB for two vectors of length n is given by this formula, right? So j is equal to 1 and 1 to n. So okay, so for j is summation of j is equal to 1 to n, vector of j into vector of b असं काहीतरी आहे. With n processors, each processor j could compute a of j into b of j. The challenge then becomes how to perform the summation in a data parallel fashion for preprocessors where p is less than n. The code would need to be changed to divide the summation task appropriately. Memory contention. A potential issue in shared memory data parallel execution is memory contention. If multiple processors try to access or write to the same memory location simultaneously, performance may not scale proportionally with the number of processors. It's true. Single program multiple data. Data parallel execution is also known as single program multiple data programming. We read that earlier. This name emphasizes that a single or same program is executed on all processors, but they operate on different data. This different data may be part of a same set of data, but it's divided into subsets, and that's why it operates on different data. The SPMD or single program multiple data or data parallel model is generally preferred where feasible due to its ease of programming and efficiency. No load in dividing the program. Use the same program, work on different data, it's fine. Right? So again, same approach. You manage the data, you structure the data well, implementation becomes easier. Speed up and Amdahl's law. Now what's this? Let's read about it. Efficiency measurement in parallel programming, or speed up, right? How do you measure efficiency in parallel programming setup? Speed up is a critical metric in parallel programming. It is defined as the ratio of the time taken by sequential algorithm to the time taken by parallel algorithm. So sequential algorithm takes 10 minutes, parallel algorithm takes 5 minutes, so the speed up would be 2, or if it is 1, then the speed up is 10 times, like that, is equal to ideal speed up for perfectly parallelizable tasks. For perfectly parallelizable task, speed up would be equal to p, the number of processors. Where speed up is proportional to p, the algorithm is considered scalable. When speed up is proportional to p, the algorithm is considered scalable. Factors limiting speed up. What are the factors that limit the speed up? Not all parts of a program can run independently or in parallel, leading to limitations in speed up. Memory contentions are there. Multiple processors are attempting to access the same memory location simultaneously. We discussed in SPMD. Data structure contention is there when different processors contend for access to shared data structures. Mutually exclusive access. Operations that require exclusive access to shared data when you are updating operations, transactions, they cannot be parallelized. Data dependency. When the result of one task must be used as an input for another task, implying a sequential order that naturally prevents parallel execution. Now, what's Amdahl's law in all of this? Amdahl's law quantifies the theoretical maximum speed up for a program given that a fraction of the program is inherently sequential. So what's the assumption? The assumption is that a fraction f of a task is not parallelizable due to constraints like those mentioned above. The remaining fraction is parallelizable. So now the formula is 1 by f plus 1 minus f by p. Here f represents the fraction of the program's execution time that is inherently sequential. This part of the program cannot benefit from additional processors. 1 minus f represents the fraction of the program's execution time that is parallelizable. Now 1 minus f upon p, this term shows that the parallelizable portion of the program's execution time is divided by the number of processors p, meaning that it is sped up by the factor of p. The denominator represents the total execution time on p processors relative to the original sequential time. It's the sum of the time for the sequential part and the time for the parallelized part. The overall speed up is the reciprocal of this relative execution time. What's the reciprocal of relative execution time? What do we mean by that? 1 upon. Now what are the implications of this? As p number of processors, or as p increases, the number of processors increase, the term approaches 0. Therefore the maximum possible speed up even with an infinite number of processors is limited by 1 by f. This is an external insight to enhance understanding of Amdahl's law's limits, not explicitly stated in the provided text but derived from the formula. So for example, if f is 10% of the 10%, the maximum speed up would be 1 upon 0.10 is equal to 10x, regardless of how many processors are added. Now Amdahl's law and data parallel SMD, what's this? Is summarization, is by definition in an ideal data parallel execution. or SPMD program. If f is 0, meaning that the entire task is considered parallelizable, in this ideal scenario, then Amdahl's law simplifies that speed up is equal to 1 plus 1 minus 0 upon p, which is 1 upon p is equal to p. This confirms that if a program is perfectly data parallel, the speed up operation is parallel to the number of processors. When speed up is proportional to p, the algorithm is considered scalable.